So in this video, we're going to talk a little about how we can use linear algebra to solve what are known as differential equations. And we're going to use eigenvalues and eigenvectors to do this. Now this is going to look a lot like modeling with discrete dynamical systems. And in discrete dynamical systems, recall that it's assumed that we have constant increments in time, which are typically 1 unit. So in this type of model where the next value of x in the next time unit is 0.2 of the current value of x plus 0.4 of the current value of y. So x and y might represent population sizes in maybe 2 different cities. And maybe what we have is, let's suppose we have a closed system. In this case we do. And what's happening here is that after each increment of time, 20% of the people who were in state X at the current time are going to remain in that state, whereas this suggests that 80% of them, this is x sub n plus 1, y sub n plus 1, 80% of the people in state X at time n move to state Y at time n plus 1. And similarly, we have that 40% of people become state X at time n plus 1, 40% of the, of the Y sub n's. And because, and that also suggests that 60% of the people who are in state Y stay in state Y. So we have a closed system. Notice that this suggests we don't have any leaks. It's not like we don't account for 100% of the people in our population. 100% of the people either stay in a state or move to the other state. Now, that's great, except that we are kind of ignoring what happens continuously. So we can't really assess what happens after, let's say this is on a yearly basis. If time is in years, then we can't really assess what is happening midway through the year, nor are we really that concerned. And so this works great if we're either not experiencing continuous changes or if continuous changes are not important. And that's fine, because looking at population sizes once a year is maybe pretty adequate. But there are things that happen on a faster scale, and we want to keep track of things during the process. So for instance, we might have a model where we're looking at the amount of a chemical, let's say this is in grams, so we have something to talk about, that is inside a 50-gallon drum, assuming water concentrated with the chemical is flowing in at 4 gallons per minute, and water is being pumped out at 4 gallons per minute. Suppose the chemical is salt and is concentrated at 2 grams per gallon flowing in. And let's assume that initially the drum is filled with clean water. Okay, so we're going to start off by defining what we want to keep track of in this scenario. We want to keep track of the amount of salt inside the drum after t minutes. Okay, so I'm just going to draw a quick little representation of this. Here's our container, and you can draw a prettier version of it if you'd like. This is just my container here, and we have something coming in, and what we have coming in is 4 gallons per minute of liquid. And we also know, and I'll just put a comma here, we also know that it's concentrated with 2 grams per 1 gallon. We'll come back to this in just a moment, but that's what we have coming in. And then maybe we have a little hole in here, and we have something that is pumping this water out. And it's, who knows where it's going, but at this point we just know it's coming out at 4 gallons per 1 minute. So if this tank is initially full with all 50 gallons, the key here is that notice that we have water coming in at the same rate we have water coming out. Now we're going to neglect the fact that if you add some sort of salt that's going to take up some volume, we're going to say that that extra volume that's taken up by that salt is going to be negligible. Okay, well, we have a continuous process happening. We have water that's flowing in, not just 4 gallons being dropped in after every 1 minute, but that 4 gallons is continually leaking in, and at the same time, we have water continuously coming out. So it's not as simple as saying that in 1 minute we'll have 2 grams of salt in there, because that water that is inside of there is actually leaking out. Now here's one major assumption that we have to make. We have to assume that the drum is being well mixed continuously. Okay, this is just a necessity to be able to construct a model, because you may say, well, there is stuff coming in, but it's kind of just hovering at the top of the water level. It's not really getting mixed in. So we're just going to assume that, if you want, you can kind of assume that there's some sort of blade in here that's kind of spinning and it's kind of mixing this all up. And we're going to assume that was a very bad drawing. We're going to assume that everything in there is instantly well mixed. If we assume that, that means that there is also salt coming out, because that water is salt water. So there's salt water coming in, and there's water concentrated with salt. Salt water coming out, and there's water concentrated with salt coming in. So the amount of salt in there is always going to be changing. And that's why it makes sense to look at what we call a continuous differential. So we can talk about the change in salt in the drum per unit time in terms of the continuous differential. So I want to analyze this for a moment. dx dt, yes, that is a derivative. Sometimes we call that a differential. And what this means is that dt is a very, very small change in time. Okay, what do we mean by very small? Well, we mean like infinitesimally small. Like so tiny that you can get as small as you want with your increment in time. And then there's going to be some very small change in salt. Okay, that's all we really need to know at this point. We don't need to get into the calculus of it. The point is that this is a continuous model. And so what we're going to keep track of is the rates of change. Specifically, the rate at which salt is coming in minus the rate at which salt is coming out. Now, we could all agree that if I had a bathtub, I'll do this real quick here, if I had a bathtub here and I was filling this up with 30 gallons per minute and I was draining the tub at 20 gallons per minute, so what would the rate be at which we're filling up the tub? Well, water's coming in faster than it's going out, and 30 minus 20 is going to be 10, positive 10. I'll put a positive on there to emphasize that every minute I'm going to have 10 more gallons inside of that tub, relative to where if I took snapshots every minute there would be 10 more gallons of volume. We'd start off with however much water we had, then 10 gallons more, 10 gallons more, until eventually that tub would overflow. Same kind of concept here. Here we're just talking about salt, and our units of dx dt, okay, this is going to be, well, the change in x, you can read this as the change in x. The change in x would be the change in salt, which is the change in grams of salt, divided by a change in time. Well, that's measured in minutes. So our model will be the net rate of grams per minute, which will be the grams per minute coming in minus the number of grams per minute coming out. So what we need to get this dx in dt, okay, in order to get this, we have to think about how many grams are coming in every minute. Well, I have 4 gallons of water coming in each minute, and I'm going to do a little tape diagram here. Let's just say that this represents 4 gallons. This is over the course of 1 minute. And every gallon, it's going to be concentrated with 2 grams of salt. So break this up into 1 gallon increments. Every one of these gallons is going to get 2 grams of salt, because that's what concentration means. This is a concentration, and that's mass how much mass per unit of volume. So each of those 4 gallons is going to get 2 grams of salt. Well, that means it's going to be 8 grams of salt per 1 minute. Okay, that's kind of the intuitive form of how we can think about this. The other way that we can think about this is by doing a unit analysis or dimensional analysis. If I have 4 gallons every 1 minute, and I multiply that by 2 grams per 1 gallon, then gallons cancel out. 4 times 2 is 8, and I get 8 grams per 1 minute. Okay, that is my rate in. So this is going to actually be dx dt, the change in salt per minute, is going to be 8 grams per minute. Okay, that the unit of that number is how many grams come in every minute. This is a rate of change minus the number of grams coming out. Okay, the number of grams coming out is a little bit more interesting because all I know is that 4 gallons are coming out every 1 minute. Now, assuming that water is well mixed, and I want to know, okay, what is the concentration? Okay, so this is, I'm going to give these names. This is flow rate. That's just how many units of volume per unit of time. And we're going to multiply that by the concentration. Concentration you can think about as the mass per volume. Grams is a unit of mass per unit of volume, which is gallons. And so in this case, just like we did before, where we multiplied by grams per gallon, I have to multiply by grams per gallon. I have to multiply my flow rate by my concentration. Well, this is the flow rate out. Now I have to think about the concentration of what's coming out. So what's coming through this outlet? Well, it's however much salt is mixed into 50 gallons. So I know that this is going to be a concentration inside of that 50 gallons. And my question is, how many grams are in that 50-gallon drum at any given moment? The problem with answering that question is we don't really know because it's a continuous process. Salt water is coming in, salt water is going out continuously throughout time. But the beauty of this is that I have a variable that says, well, at any moment, after t minutes, there is X amount of salt. By the way, this should be in grams. There are X grams of salt inside of there. So the outflow rate is always going to involve a variable concentration. It's going to be the number of grams inside the tank, which is X, divided by the number of gallons inside of that tank, which is 50. Okay, so X over 50 will be grams per gallon. Again, there are X grams in there, and they're well mixed within that 50 gallons. So every ounce of water that you pull out of there, we're assuming that it is equally concentrated. And so if you multiply these together, you get the cancellation. Again, you can kind of do this tape diagram, except in this case, it's going to be X grams, X grams, X grams, and that would be 4x grams per, but this is not 4 gallons, it's per 50 gallons. Okay, so 4x over 50, which I'm just going to go ahead and reduce. I think this comes out to 0.08x. So if I do 4 divided by 50, it just makes it a little bit easier, comes out to a whole number. So, putting the pieces together, this dx dt, the change in salt per unit a minute is the amount of salt coming in, which is 8 grams per minute, minus, again, this is already in grams per minute, the number of grams per minute coming out, which is variable, it's 0.08 times x. So the model looks simple enough, and yet what we're ultimately going to want to know, and we're going to evaluate in a minute, is how do we get x as a function of time? Okay, so we have to solve this. You might remember integration comes into play where we work backwards to take a derivative and get the original function, but there's going to be an easier way. We're going to do a little bit more modeling. Suppose the concentrated water that exits the first barrel flows into another 50-gallon drum, initially filled with clean water. Water flows out of the second drum at 4 gallons per minute and flows into a third container, which we will ignore. So we have our second drum here, okay, and we have something flowing in, right? What's flowing in here? Flowing in here is what's coming out of the first drum. I'm going to make it small, it's not the actual size of it, but it's what's coming out of here as far as the amount of salt. Now, in this case, I already have that. That's going to be my 4 gallons per 1 minute multiplied by, there's going to be X grams in it distributed among the 50 gallons of drum number 1. So that's what's coming into tank 2. So that means that dy dt, I'm going to let y be the amount of salt inside the second drum after t minutes. And by amount, we mean grams. And again, this is still in grams per minute. That's going to equal 0.08x positive because it's going in. It's increasing the grams inside of the tank minus what's coming out. Okay, so now we're going to do a very similar analysis. Well, the flow rate out is still 4 gallons per 1 minute multiplied by the concentration of grams per gallon. Well, how many grams are inside of tank 2? Again, we're going to assume everything's well mixed in here. And there, therefore, are going to be y grams inside of that drum at any given moment, divided by the number of gallons in that drum, which is always going to be 50 since water's flowing in at the same rate that it's flowing out, and it's initially filled with clean water. Okay, so divided by 50. And so if you simplify that, which is going to give us grams per gallon, it'll be 4y over 50 grams per gallon, which equals, again, 0.08, but in this case, y grams per gallon. And that's going to be what's coming out of tank 2. It's kind of like we're starting to see a linear model kind of emerging here. Except the linear model, what it inputs is quantities of salt, and what it outputs is the rate of change of salt in grams per minute. Okay, before we learn how to solve this, and so again, what we want to get is we want to get y as some function of time. So what is that function of time? Let's make one more change to our model, and then we'll show how we can use eigenvalues and eigenvectors to solve this. Well, let's suppose that the first tank already has 100 grams of sugar in it. Suppose the inflow into the first drum is fed the output of the second tank. Okay, so what I'm trying to get at here is, let's suppose we have our 2 tanks, and we're going to modify the first tank in the way that we're not going to have the concentrated water coming in, but it's actually going to be the output of the second tank. So here's our second tank or drum. And so what we're going to assume is that instead of the inflow being this source that had 4 gallons per minute with 2 grams per gallon, we're going to nix that, and instead we're going to assume that the only rate of inflow is from the first tank. So, in other words, let's imagine water going this way, and also the water flowing into tank 2. Water going this way. And we're going to assume that, these 50 gallons already has 100 grams of sugar in it. Here we also have 50 gallons. We're assuming that's still the clean water. And what we have going out of drum 1 is 4 gallons every 1 minute multiplied by, there are X grams inside of here. And over here in tank 2, drum 2, there are y grams. And so the only interchange in the change in x and the change in y is this loop that cycles back and forth. So what I am imagining is happening, and again, assuming everything is well mixed instantly, that this 100 grams will eventually become diluted inside of the clean water, and that eventually, once they cycle into each other long enough, that we'll reach sort of an equilibrium. So let's model this. We have 4 gallons per minute going out. That water is concentrated. Okay? You don't want to say 100 grams per 50 gallons because, again, continuously you have clean water coming in at first and salted water going out at first, and it's a continuous cycle. So at any given second, or any given minute, we can just say there are X grams. And we want gallons per minute times grams per gallon so that we get grams per minute. Okay. Well, gallons, there are 50. Now, as far as what's coming in, that's what's going out of tank 2 at 4 gallons per 1 minute, multiplied by how many grams over how many gallons. Well, there are y grams in there distributed among 50 gallons, and again, our units cancel out, and we are in units of grams per minute. So once again, I'm going to be able to assess the rate at which grams are changing in drum 1 in units per minute. Well, that's going to be the what's coming in, what's coming in is this 4 times y divided by 50. Now, 4 times y divided by 50 is 4/50ths y, and that's going to be 0.08 times y. That's what's coming in. Now, what's going out, minus what's going out, is the 4/50ths of x, 0.08x, and similarly for the rate at which salt is changing in the second tank per unit of time, well, it's what's coming in, which is the 0.08x, minus what's going out, which is the 0.08y. Now, because I'm going to want to put this, as you can tell, into matrix form, we are doing linear algebra here, I want to make sure that my variables are in the right order. So negative 0.08x plus 0.08y, and then dy dt equals positive 0.08x minus 0.08y. Now I want you to note one interesting fact, and that interesting fact is this. If you added up dx dt plus dy dt, in other words, that's the net change in salt in drum 1 plus the net change in salt in drum 2, you'll get 0 plus 0 equals 0. This is analogous to our closed system where we had people only moving between the two states. The only difference here is that we're not accounting for what stays inside because we're not modeling the size, the number of grams, we're modeling the change in grams. That's what is different here. Okay, now if we were to wrap our two, you can kind of see where we're going with this. If I were to wrap our two equations in a vector form, so dx dt dy dt is our vector on the left, equals the vector consisting of the two expressions for the equation on the right, we could write a matrix equation here. And this matrix equation will have our two differentials, a matrix with our coefficients, and then a matrix, a vector with our variables. So I'm going to call this vector x right here, as we have been calling it before. I'm going to call this matrix A. Now this vector right here, if you notice that if you take, these are both functions. X and y are functions of time. Why are they functions of time, and what do I mean by that? Well, what I mean by that is that x and y are changing over as time passes by. Okay, that's what we mean by x and y are functions of time. And the reason they change is because of the continuous inflow and outflow of water from each of the two systems. So that means that if you were to take the derivative of a vector, and guess what? Derivatives of vectors, just take the derivative of both of the components. So the derivative of x, well, that's a function, is going to be dx dt, and the derivative of y is going to be dy dt. So that means since this vector is called x, it makes sense to call this vector the derivative of the x vector. Now, whether you write it as d dt of x or dx dt, it's the same thing. This kind of implies that you're going to take the derivative of the vector. This kind of implies that the vector has already been taken the derivative of. That's a small distinction there. So we get this matrix vector product that outputs rates of change. And the question is, well, how do we get the vector x of t? We want to solve for x of t. In other words, I want an equation for little x, the number of grams in drum 1, and I want a function little y of t for the number of grams in tank 2. Well, here's how you do it. Any system of first-order differential equations of the form the derivative of x equals ax, where a is a 2 by 2 that contains constants, has the following solution. Now, this doesn't have to be a 2 by 2. This states lambda 1 and lambda 2, v1, v2 would only be for a 2 by 2. This could also be for a 3 by 3, or a 4 by 4, or a 5 by 5 system. Is going to equal x vector equals k1 e to the lambda 1 times t times eigenvector 1 plus k2 e to the lambda 2t times eigenvector 2, where lambda 1, lambda 2, v1, and v2 are all the eigenvalues, eigenvectors of A. And these k1 and k2, these might look familiar from modeling with the eigen expansion or the diagonalization decomposition theorem. K1 and k2 are arbitrary constants whose values are determined by the initial conditions. X of 0 equals some value, some x naught, and y of 0 equals y naught. So what we mean by x of 0 is this is time, and this is the salt amount at time 0. This is time, and this is the y value at time 0. So you could also write this as ordered pairs 0, comma x0 and 0, comma y0. Okay, so we can now solve this model since we have the A matrix. Our A matrix is negative 0.08, 0.08, 0.08, negative 0.08. This is our matrix that we want to find the eigenvalues of. We will give this a justification in a moment to show you why this is the solution and how we know it works. But for now, let's just go ahead and find it. So here I've produced those using Wolfram Alpha, and we have lambda 1 is negative 4/25. Negative 4/25, I think, let's see, we could probably just leave that as a decimal. Yeah, that comes out to 0.16, well, negative 0.16. And so using the theorem up here, x of t vector, or x vector equals, I just put the x of t on there to emphasize this is going to be a function of time, is k1 e to the lambda 1 times t times v1. And v1 is the vector, let's see, 1, negative 1, 1, plus k2 e to the lambda 2t, so this is lambda of 0, times the 1, 1 vector. Okay, any eigenvector, any multiple of an eigenvector is an eigenvector, so we don't necessarily have to have these ones because k1 and k2 will be computed based upon our initial conditions. Okay, so what I'd like to point out here is something interesting. The diagonalization decomposition theorem was actually a little bit, I'll call it diagonalization decomposition theorem. It said that x is equal to k1 lambda 1 to the t times v1 plus k2 lambda 2 to the t v2. Now, these were our lambdas, but now we have exponential functions, and our exponentials are, well, they're in the exponent. But the one thing that I think is valuable to note is because we're dealing with continuous functions, Euler's constant E is a sign of us working with continuous growth or continuous change. You might remember the Hurt formula, the financial formula where you have continuous compounding. Yeah, that's the same E that we see in there, and our R in this case, our R's are the lambdas. Okay, without further ado, so what we have here is we have x of t, y of t inside of that vector, our amount of salt in drum 1, or salt in drum 2, equals, well, this will be negative 1 times k1, e to the negative 0.16 t, plus 1 k2, e to the 0t. Well, e to the 0t, by the way, is just 1. So in this case, that, equal to 1. So I think I'm going to go ahead and leave this e off right there. It's just going to end up being plus k2. And then we'll have k1 e to the negative 0.16 t times positive 1, which is just k1 e to the negative 0.16 t, plus k2 times 1, which is plus k2. And there we go. We have our two differential equations. The only thing that we don't know is what is the value of k1 and what's the value of k2. Well, our initial conditions, our x of 0, we said there's 100 grams of salt in there initially. Tank 2, from the get-go, that one had clean water, which means that it has 0 grams of salt initially. Clean water. And this had 100 grams of salt. Excellent. Okay, those are the conditions that we'll plug in. So when time is 0, x is 100, and when time is 0, y is 0. So we get 100, 0 equals, and if I plug in e to the 0, or e to the negative 0.16 times 0 times t, I just plugged in 0 for t, excuse me. Well, that's going to equal 1. So I'll just have negative k1 plus k2, and here I have k1 e to the 0 is k1 plus k2, and you can see we have a system of equations, negative 1k1 plus 1k2 equals 100, 1k1 plus 1k2 equals 0, and so now I can build a matrix. This is solving another system of equations here, negative 1, 1, 100, and 1, 1, 0. This is for k1 and k2. And I can solve this. And let's see, what will I get? I think this will reduce to (1, 0), negative 50, and 0, 1, positive 50. So that implies that k1 is negative 50, k2 is positive 50. So remember, my goal is to write equations for the amount of salt in drum 1, which is negative of k1, so negative 50, positive 50, e to the negative 0.16 t, plus k2, which is plus 50. And then y of t will equal k1, which is negative 50, e to the negative 0.16 t plus 50. Now we're going to graph this, we're going to see what's happening in these two drums, but I want to just do a quick analysis. As t gets larger and larger and larger, as t approaches positive infinity, note that e to the negative 0.16 t is the same thing as 1 over e to the positive 0.16 t. So as time gets bigger and bigger and bigger, this thing is going to approach 0, right? Because 1 over e to a larger and larger power will be 1 over a large number, which gets closer and closer to 0. So that means that that first term in both equations will sort of become negligible as time becomes large. X of t will therefore just equal 50, and y of t will therefore just equal 50. Now these are grams, so this is suggesting that as time goes on, the amount of salt will evenly distribute between the two drums. And that should kind of make sense because it's the highly concentrated water flowing into clean water, and then the clean water flowing into the concentrated water, and eventually those two drums will be very, very well mixed together. And so it would make sense that since they're the same drum size, we would expect the same amount of salt in them. Now, if these were different drum sizes, we would just expect the larger drum, even if it had all the clean water, to get more of that salt. We have 100 grams per 50 gallons initially. 100 grams per 50 gallons is 2 grams per 1 gallon. 2 grams per 1 gallon, and there are 100 gallons total. That means we would expect each the total to be 100 grams between the two drums, 50 in each tank. Okay, anyway, rambling on. Let's go and check out our graph. So the red curve is for the first equation, the blue curve is for the second equation. We can see that that first drum begins to lose salt exponentially and then flattens out at x of t equals 50, whereas in the second drum, the amount of salt increases upwards towards 50, because again, those first two terms are becoming more and more negligible. And so in the long run, we can say, and not only can we say that in the long run what's going to happen, but we can see what happens all along the way. Like maybe we want to turn off the pumps after the amount of salt in that second drum reaches, say, 25 grams. And that's going to happen at time 4.332. Well, at time 4.332, that would mean that here we would have to have 75 grams, which is right around 75. So we could answer other questions of things that happen in between, especially if these were some special types of chemicals we were mixing and we wanted to achieve an exact concentration. This is what we could do with these things that we call differential equations. This is now just an introduction to this idea. It is possible to have complex eigenvalues. There is more of an analysis here, but the goal is just to see that we can use linear algebra concepts to help us in continuous mathematics like differential equations.